This is a podcast of Costing the Earth from the BBC. For full terms and conditions, please go to the website at bbc.co.uk.
This is a lovely 1976 vintage Bristol 603S. It's been well looked after and it's running very smoothly. This car is the same age as the oldest of Britain's working nuclear reactors. Today on Costing the Earth, we're going to take a spin through the recent history of nuclear energy and ask if complex and potentially dangerous machinery from before the age of punk really ought to be supplying our power in 2016.
Newsbeat.
We're starting today with one of the most expensive projects of all time. The government's given the go-ahead for an £18 billion nuclear power station in the UK.
After weeks of uncertainty, the government has given the go-ahead to the controversial Hinkley Point nuclear project in Somerset.
That announcement was the one the nuclear industry had been waiting and wishing for many years. Finally, our ageing fleet of nuclear reactors could start to be replaced.
I was delighted that this decision was made. It's been a long time coming. The UK needs the energy, it needs the electricity generation. We're really running out of options.
Hinkley Point C will deliver up to 25,000 jobs during the course of its lifetime, delivering a huge construction project which will be the biggest in Europe.
It means a massive amount because this is about the next generation of nuclear power stations. We've had them in this country for 60 odd years. They've produced reliable, consistent amounts of electricity, but they're all getting towards the end of their lives. They will all retire by the mid-2030s, all but one by 2030.
Tom Greatrix of the Nuclear Industry Association and Matt Burley and Brian McConnell from Nuclear South West. The government may have given the go-ahead, but some experts can see plenty of obstacles still in the way of the construction of Hinkley C. First, Simon Taylor of Cambridge University, author of The Fall and Rise of Nuclear Power in Britain.
There are, I suppose, two ways in which Hinkley might fail to happen. One is that there is a challenge at the EDF board end, which could, in theory, reverse or cancel the original board decision to approve it. The other possibility is that it is delayed pending the completion of the same reactor type in France at Flamanville, and if that develops problems that appear to be more serious than expected, it could be that Hinkley is delayed indefinitely or even cancelled.
The problem that Simon alludes to is all about the metal parts that were built for EDF's Flamanville reactor that's being built in France. John Large is an independent nuclear consultant.
Well, what has been recently discovered in France is that the parts of the reactor pressure vessel for the Flamanville 3 reactor, this is the same reactor as designed for Hinkley Point, have got what's called macro segregation, which effectively means they have a slight excess of carbon. The French looked into this and then discovered that this originated in a forge at Creusot in France. Hinkley Point, the contract that the British government has, is that Flamanville will be up and running by 2020, and it'll be running for a long enough period to prove the technology. Otherwise, the British government's credit guarantees, which EDF and the Chinese can draw upon to build the Hinkley Point reactor, will be withdrawn. So, unless Flamanville is completed and demonstrates the technology, Hinkley Point will run out of British government funding, and this could be very significant indeed.
Any delay really does matter because 5 out of 8 nuclear power stations that we rely on today in the UK are already operating beyond their planned lifespan, and that, as we'll find out in this week's Costing the Earth, makes some well-informed people very nervous.
Well, what we know is that these reactors are ageing, so certain parts inside are deteriorating, particularly the graphite core. And that means there's a change of risk. There's a change of the acceptability of whether these reactors will function when there's some adverse event like an earthquake or a boiler failure. So what we're doing is chipping away at the margin that the original designers accepted for the risk of accident.
The reason that we're running these old reactors, extending their lives as far as possible into the future, is clear. A yawning gap in our electricity supply. Simon Taylor from Cambridge University's Judge Business School.
The risk of running out of electricity, one would have thought would be something that no government would want to get remotely close to, and yet we are really quite close to that happening. It doesn't necessarily mean the lights would go out, but there's a real risk if we have a cold winter in the next couple of years that industrial customers may be required to shed load, which means essentially switch things off. And it's extraordinary that's even conceivable in a modern economy.
How likely, if you're a betting man, is that to happen over this winter?
I think the National Grid has done an excellent job for many, many years, and they will do whatever they possibly can to avoid that happening. But it only takes a colder winter than average. The last few winters have actually been warmer than average, and one or two accidental breakdowns in bits of equipment around the system.
The potential problem was demonstrated in September when the price of electricity that power companies had to pay the generators spiked massively. Zoe Double is head of power at the energy market consultants ICIS.
On the 14th of September, we had a couple of unplanned outages. There was one plant that took a while to come back from its planned maintenance, and that wasn't expected by the market. And then the other plant problem that we had was an unplanned outage where a plant went offline. There wasn't a lot of wind generation, and actually in recent years that's really become a factor on the UK markets. If it's a windy day, it can really drive down prices, and of course vice versa. Now, altogether, that didn't actually add up to a huge amount of generation, but because we've got such a tight supply margin at the moment, and this is something that National Grid has been warning about, we actually saw a rather alarmed reaction from the markets. And in fact, we saw some of the most expensive power ever changing hands since ICIS began covering the market. So in mid-September, the ICIS Power Index is around £43 per megawatt hour. And we actually saw the price of electricity changing hands at £200 per megawatt hour. And this is the most expensive trade, baseload electricity trade that we've ever seen on the markets. And that does imply that the markets were particularly concerned about our supply margin and were expecting further disruption.
Days like the 14th of September are unusual, and they don't result in an immediate increase in the price we pay for our household electricity. But as coal power stations close and ageing nuclear power plants become less reliable, the national grid becomes ever more reliant on emergency backup, including expensive and dirty diesel generators.
All ageing plant tends to become more unreliable. It means they don't always come back on when they're expected to after maintenance shutdowns, or they just develop unexpected problems and have to be shut down prematurely. These are risks, and they're not even easy to quantify because we don't have a lot of data on these reactors. There aren't enough of the AGRs around the world. They're all in the UK. There aren't enough to kind of estimate how likely these things are to go wrong. You know, it's not a comfortable situation to be saying, yes, they will become more unreliable, but we don't know how much.
This is Costing the Earth on BBC Radio 4. With my vintage car, if something goes wrong, it's normally fairly straightforward to keep it running smoothly. You can lift the bonnet and you can check the oil and the fan belt. But with nuclear reactors, it's unsurprisingly very different. The highly radioactive core makes it tough to lift the bonnet, and any unexpected faults can shut the plant down for a long time. These unplanned outages, there were 62 between 2012 and 2014, put stress on the national power supply and can massively increase the price of electricity. But the crucial question is about safety. Are these unplanned shutdowns just one symptom of machinery reaching the end of its life? Is it safe to be running complex reactors long past their expected lifespan?
My name is Alan Jeffrey. I'm Assistant Coordinator of Stop Hinkley, and I've been campaigning against the building of nuclear reactors at Hinkley for the last 35 years. We're just in front of the Hinkley reactors, the old British reactors, the A station and the B station. The B station has now reached 40 years, which is 5 years of extension of its life beyond its planned designed life, and EDF want to extend it for another 7 years until 2023. Is this really a gamble with public safety? because there are several key problems with extending the life of these reactors. Hinkley B, as I say, even way back in 2005, the Nuclear Installations Inspectorate was very concerned about the structure of the central core of these reactors. If you extend the life of mechanical, industrial technology, as it gets older and older, there's more chance of breakdowns, there's more chance of parts wearing out, and there's more chance of accidents.
So I've just walked into the control room, not the real one at Hinkley B, but a mock control room. There are several large arrays of panels with knobs on. They look pretty much of its time, 1970s, with, if I can, just turn a button. Yes, they go either right or left, anti-clockwise or clockwise. Thank goodness they're not real. Above them we have an array of computers.
Yes, it allows us to maintain the as-designed ergonomics, and then of course overlaying that with completely up-to-date modern digital electronics and computer screens and models allows us to get the best of both worlds.
Yes, but I could see Homer Simpson wouldn't be out of place here.
We love having Homer Simpson as a means of helping us describe the nuclear business. It's been a treat those last 15 years.
I'm looking down on Reactor 4 at Hinkley B from the viewing gallery. In front of me is a huge area, as long as a football pitch, maybe as high as one and almost as wide as a football pitch. There's a grid of 308 squares. Those are, I understand, each of the columns for the graphite columns underneath there. And there's about 23 metres high below there, but there's another space about 23 metres high where they can lift out the fuel whenever they need to, so it's actually incredibly deep. The graphite core of a reactor is where the nuclear reaction takes place. Here at Hinkley B, it's made up of 6,000 graphite blocks. Around half of those are a metre tall, with a bore or channel running through each block. Around 200 of those channels contain rods of nuclear fuel. If anything goes wrong, control rods are inserted between the channels to dampen the nuclear reaction and shut down the reactor.
Here we are talking about graphite. This is graphite. This is a pencil. So we're talking about a nuclear reactor that has a piece of graphite in it like that. So it's not a really engineering material that you can rely upon. It's neither elastic, it doesn't bend, and it's not particularly strong.
Graphite is at the core of Britain's nuclear reactors and at the core of growing concerns. The bricks are cracking. John Large is an independent nuclear consultant who helped develop the graphite core and the fuel systems in advanced gas-cooled reactors.
The graphite core itself is an assembly of several thousand bricks, loosely stacked together. And the original design was that core would never foul. So there was no facility to replace any individual bricks if they became damaged. So the concern is that here you have a feature of the reactor, the very heart of the reactor, the fuel core, but now it's undergoing progressive failure. There are physical changes occurring in the core, in the individual bricks, this cracking and fracturing of the bricks, that must result in some loss of the residual strength of not only the brick, but the core overall.
We used the Freedom of Information Act to request a number of documents for this programme. One paper from the Office for Nuclear Regulation reveals that 1/3 of the channels inspected at our two oldest reactors, Hinkley B in Somerset and Hunterston B in Ayrshire, contain what they describe as significant cracks. Brian Cowell is Director of Nuclear Operations at EDF, the French company that runs all of Britain's commercial reactors. He says that those cracks were anticipated at this stage in the reactor's life, and it's safe to operate for years and years to come.
The massive body of evidence and analysis that we are doing, and of course are sharing with the regulator and with the expert panels, is telling us that our predictions are accurate, that we are within the bounds of where we should be at this stage in the evolution of the reactor cores, and that our life extension assumptions to 2023 in this reactor are very much underpinned. And in fact, we are looking to extend life further if we can. The analysis that we have suggests that we can have more than 1,000 axial cracked bricks and still be operating with massive margins of safety, where the reactors will still operate safely and shut down safely.
1,000 cracked bricks would exceed the current safety limit set by the government-appointed Office for Nuclear Regulation. That would prevent EDF extending the life of the oldest reactors even further. However, the regulator, we discovered, is considering changing that limit. Mark Foy is the ONR's Deputy Chief Inspector. Now, you set limits for the percentage of bricks that you'd be happy to be cracked, and that was 10%. But the documentation we have here shows that you're more recently considering changing that to 20%. Can you explain that to me?
Yes. The original safety case that was developed by EDF was provided on the basis of 10% cracking across the bricks within the reactor core. As experience is gained, analysis and research is undertaken, it allows EDF and ourselves independently to gain a more informed view and a more accurate view of what is acceptable and what isn't acceptable. They have now provided us with a case for allowing 20% extent of cracking within the graphite bricks. That is based on the analysis they've undertaken, the samples that they've taken from the reactors themselves, and the inspections they've undertaken as well, and the research that they're doing independently with regards to the impact of seismic, because seismic could disrupt the core and prevent control rods entering it. So they've done lots of analysis. That is provided to us in form of a comprehensive justification, which we will assess to see whether we're satisfied that it's safe to operate.
So you're considering that at the moment?
Yes, we are.
The ONR is also investigating a very specific and more concerning form of cracking, fractures with a real potential to force the shutdown of the reactors.
The root of the keyway is a square slot that holds that brick to the adjacent brick, to the bricks underneath and to the bricks on top. These keyways are beginning to fracture, so it becomes a very loose stack of bricks.
These keyway roots that hold the brick of the core together are acknowledged to be the crucial limiting factor on the lifespan of a reactor. Professor Paul Bowen of Birmingham University sits on the Graphite Technical Advisory Committee for the ONR. He says these cracks could potentially prevent the entry of the control rods, which are vital in shutting down the reactor.
We have to assume that when the bricks crack, the core becomes a little bit floppier, so it starts to distort. And very importantly, the function of the core is to allow, or part of the function of the core, is to allow control rod entry in the event that you wish to shut down the reactor. If the core distorts too much, you can imagine trying to feed anything, or I don't know, perhaps a drinking straw tube into a beaker. Something gets in the way of that drinking straw because the actual medium you're trying to push it through is actually becoming blocked. So if you have too much of that and too few of the control rods can be guaranteed to enter, then you contravene some of the principles of safety for the nuclear reactor.
7 of these keyway root cracks have now been discovered at Hunterston B in Ayrshire. John Large believes their presence casts doubt on the safety of the reactor in the event of an emergency, like an earthquake.
So now we have a cracked and deteriorated core that's lost its residual strength, and we don't know by how much. Then some of the design case accidents will test the core. Now, one of those is a seismic shake, where the whole core is wobbled, rather like a jelly on a plate, so you get lots of forces in them. And we really don't know how the core will react in those extreme conditions. If you have the core suddenly misalign, and the fuel modules get stuck in the core, that means the fuel will raise in temperature and undergo what's called a melt. So the fuel will start breaking up, the clad will break up, the stainless steel clad will break up, and the ceramic oxide pellets will start breaking up and release fission products. And it's that fission product, the radioactivity, if it gets into the gas stream, and if the reactor is venting because it's overpressurized, then you have a release to the atmosphere and you have a dispersion and contamination problem for communities nearby or afar. So that's the sort of worst case scenario you can have.
And you think it's a credible
scenario
at the moment?
Of course it's a credible scenario.
The Office for Nuclear Regulation agrees that the keyway cracks could compromise safety. One of our Freedom of Information requests yielded a document written just after the cracks were found at Hunterston B. Your own documentation says the discovery of keyway root cracks invalidates the previous safety cases. What does that mean?
During the periods of outage, they discovered the keyway root cracking. That then meant that EDF had to consider the implications of the onset of keyway root cracking in its safety case and consider what evidence was necessary to present to us as the nuclear safety and security regulator to satisfy us that it was safe to continue operating that reactor. So they developed the safety case and also called upon the resilience that was being provided by the superarticulated control rods and the nitrogen injection shutdown systems.
Those superarticulated control rods and the nitrogen injection that Mark Foy mentioned are extra safety systems brought into Hunterston and Hinkley B to address the extra risks posed by the Keyway route cracking. The new rods are bendy, making them easier to squeeze into a distorted core, and an injection of nitrogen could buy several hours of invaluable time in the event of an accident. However, a concern remains. We really can't be sure how many of these potentially dangerous Keyway route cracks there actually are in Britain's reactors. John Large explains.
Well, the difficulty is this. To examine where the cracks are, you have to take the fuel out of the reactor. That's quite a job. Then you have to put a camera down to inspect the inside of the bore. But these Keyway cracks are on the outside of the brick, so you can't actually see the Keyway crack or its development as it starts. Those bricks that have got development cracks in, if you have an adverse condition that stresses the core, those cracks can just flip away quickly. You know, I can demonstrate this with a piece of paper. Look, take a piece of paper, you put a little crack in, like this. That's fairly good. As the crack grows, it shatters completely.
As John Large points out, it's very hard to inspect the channels in which the fuel sits in what are the oldest working commercial reactors in the UK. Around 10% are checked each time the reactor is shut down. That means there may be Keyway route cracks that have never been seen at Hunterston or Hinkley B. In the absence of a full visual inspection, a mathematical model is used to work out the likelihood of these cracks in particular parts of the reactor. The trouble is that this model has already been shown to be flawed. Paul Bowen from Birmingham University.
It is fair to say that the exact timing of the cracks, so when would we see a first Keyway route crack, the industry has not, I say we the industry, but my independent committee looking at this, they haven't got that exactly perfect. They would argue, not sure we'd necessarily accept this at the moment, but they would argue that that's because their models were biased more towards making sure they were using a narrow window for initiation of the cracks and a very fast rate for the proliferation, the number of cracks that would then appear. So, two things. Yes, one, the precise timing of the first crack seen was not perfect. And you are correct, there are various layers, all of which are highly irradiated within the core, and the industry had indeed argued that layers 4 and 5 would actually be the most vulnerable layers, or the ones in which cracks should first appear. And you're absolutely correct, the first crack to appear has been in layer 6.
So how surprised was the nuclear regulator when told by EDF about the discovery of these cracks at Hunterston B?
We're not surprised. The onset of Keyway route cracking was anticipated, and because of the concerns around the statistical analysis and the theory, there is a requirement there to do inspections. And the inspections are the basis and the evidence of continued operation.
It's clear to me that the predictive model relied upon the ONR is not working. It's not telling the ONR and its experts where the cracks are likely to occur. So they can't predict the strength of the core. And more to the point, they can't predict where to put their investigative probes down to see how the cracking is going on. So they're in the dark. Now, who wants to be in the dark when you have a nuclear reactor out of control?
Both EDF, the company operating our nuclear reactors, and the Office for Nuclear Regulation insist that safety is their first priority. But it might be difficult for people living close to these reactors to understand why the definition of safe seems to be changing. EDF wants to run the reactors longer with more weight loss and cracks in the bricks. How can we be confident in the limits of the safety case if you keep allowing EDF to keep changing the goalposts all the time?
We are a completely independent nuclear safety regulator. We hold the industry to account against the most stringent standards. If we believe that the justification that is presented to us from EDF isn't robust, doesn't present a really good, rigorous analysis and assessment of the condition of that reactor, and presents a well-structured safety argument, we will not allow the reactor to start up.
So, is it safe to keep running these ageing reactors? Brian Cowell, boss of EDF's nuclear operations, is very confident. So at the moment we're looking at a lifespan for Hinkley B of half a century, basically, when originally it was designed for 30 years. Are you confident that it will always be safe?
Only last month we found one of our reactors had broken the world record of the longest continuous safe, efficient run of any reactor anywhere in the world. And my job and my team's job is to maintain that fantastic safe operational performance right out to the point where we believe actually we're starting to erode margins, we're going to stop, and we will absolutely do that.
But your job also is, as you've been doing, is to keep pushing those safety margins, the 10% cracks going to 20%, the 15% weight loss going up.
As I keep saying,
wouldn't it be better just to leave things as they were originally planned, safer?
Our intent is to make sure that the original design safety margins are maintained. As you get more and more experience with operating this fantastic technology, these engineers and scientists are able to be much more confident, and therefore some of the very conservative assumptions that were built into the original assumptions and cases can actually be revisited, and we can say, well, actually no, we know now after 40 years of operation that conservative assumption was actually too pessimistic. And that, of course, then folds through into your safety case, which you then have to do your internal assessment on, including an independent nuclear safety committee. And once we've done all that, we will then present it to the Office for Nuclear Regulation, who have their own independent assessment of it. So the fact that these cases and limits, which, as I said, are not boundaries between safe and unsafe, they're simply limits, that it is not a surprise at all that as we get more and more experience, we're able to flex them. And that's exactly what we're doing.
The very safest option might be to shut our oldest reactors down before the core cracking gets worse. Do that, however, and Britain loses a significant percentage of our power. So our final question for nuclear engineer John Large: does he think we should shut them down tomorrow?
I'd have a greater and publicly informed review about this. It's the local communities that have to live with these reactors and live with the risk. It's all very well for technicians and scientists to say to the public, trust in us, but the public doesn't trust in us anymore. After all, the public have to live with this, they have to live with the risk, so they should be informed about the risk.